Welcome to another coding session where I'm creating a new programming language from scratch. Today I'll be implementing garbage collection, and I want these videos to be kind of accessible to people who have general programming knowledge. So I'm first going to give a quick introduction of how does memory management actually work, like how does memory work, how do you request more memory from the operating system. And then we'll look at how C does memory management with like manual management via allocators, and how do garbage collected languages work. So memory is a resource that the operating system manages, and you have these different processes running on your computer, like your browser, your games, your your editor, your terminal, all of the different programs you have. And those have isolated memories. So for example, some game can't access the memory of your browser, because the memory stores the data of these processes, and you don't want any random game you play to be able to access your banking details, for example. So that's why all of the processes have separate memory. Right. So maybe let's look at how to request memory from the operating system, and then work our way up from there. So the modern computers, they basically consist of two very important components, the CPU and the memory. The CPU can actually execute code. There's hardware wires that can add numbers, subtract numbers, and so on. And the memory is good for storing huge amounts of data. So these are the RAM chips that you put into your computer if you build one yourself, or like that built into your computer if you have a laptop that's integrated. Right. The CPU itself also has some kind of storage, but it's very limited. So the CPU only has things called registers, and they have weird names like RAX, for example, and RBX, RCX, RDX. These are the registers for my computer, which is x86-64. So of course there are different CPUs by different people, where the registers are named differently and they support different operations. The operations, by the way, are called instructions, and they are also documented. So because this is an Intel CPU, there's this nice manual where all of the different instructions are in there. So for example, there's an instruction for taking the square root of something. There's an instruction for adding two numbers. There are instructions for subtracting one number from another, for multiplying two numbers, for dividing numbers, and so on. Yeah, for comparing numbers as well, all of that. And there were also instructions for moving data between these registers, and moving data from the memory to registers, and from registers to memory. And let's actually actually a small little assembly file. Assembly files have the extension .s. Oh yeah, I actually started doing that before. So here we have a test.s file, and the concrete assembly format differs a bit depending on which program you use to compile this into an executable. And we'll use the FASM assembler, which is the flat assembler. Yeah, it's just some version of an assembler. So for FASM, there's this, basically you tell it which kind of format should this have, and ELF64 is, you don't need to worry about it, but it's basically a format for executable files that Linux understands. And we'll also have segments, which are like memory regions, because the instructions that the CPU needs to execute, they are actually part of the memory. So the instructions are somewhere in memory, and they need to be readable and executable. So memory can be readable, writable, and executable, and some architectures have limitations. So for example, on Apple CPUs, I think memory can't be writable and executable at the same time. So you can write to memory, basically create instructions there, and then you can tell the operating system to make that memory not writable anymore, but make it executable, and then you can jump there and those instructions get executed. Yeah, I'm just going to put a few instructions here. So for example, moving a value into a register works. Like this moves the value 4 into the register RAX. Yeah, so now we can compile that, and we have a test executable, which fails when we execute that. And that's because the CPU actually executes this instruction, but then after that, there's just garbage in memory. And at some point, it tries to execute the instructions, it tries to interpret the memory that comes after this as new instructions, and that fails at some point. Yeah, this test file, let's actually look at this. So this is an executable, which means you can run this. And you can also, I think it was -x. Yeah, look at what this file tells the operating system to do. Oh yeah. So this is actually like a pretty small file. This is the entire content. And this content tells, like part of this content tells the operating system, if you want to execute this file, what should you do? And the object dump command presents that information in a way that you can also read. So it has a bunch of headers, which basically tell the operating system, hey, when you want to execute this file, you should load the content from position 00000 in this file. Please move that into this memory address. So you can see that this is like 4000000. And the file size, like the amount of data that you should move, is this, which is interesting. Like 7F, I think is, oh yeah, that's exactly the size of the file. Sure. So basically the operating system moves the content of the file somewhere in memory, and then it just starts executing the file at this position. So at 4000078, we can look at what's at 787, 1 byte, 2, 3, 4, 5, 6, 7, 8. Okay, this. So the CPU actually starts interpreting this memory as instructions. Yeah. So our move instruction, move 4 into RAX, is somewhere in here. And I think we can actually see that. So perhaps this is like the move instruction, or this is the move instruction probably. And here is a byte that's just 4. If we change this to 5, we'll probably see a 5 in there. So yeah, assemble this. Hang on. Yeah. And yeah, now there's a 5 in the binary. So these instructions are just converted into this dense encoding format. And yeah, when we execute that, the CPU will execute this move instruction, and then it will interpret this as another instruction, and this as another instruction, and so on. Yeah, and that kind of doesn't work. Also, let's talk about what this V address means. So this basically tells the operating system where to move the memory to, and this can't collide with other processes, like the browser, for example, or our editor, because each process has its own address space. That's what the V stands for. It's the virtual address space that's specific to this process. Right. Okay. So what do we need to do to make this program not crash? There's a bunch of syscalls that basically say, okay, now I want to do something that requires the help of the operating system. So, of course, those are also documented. And these are the the syscalls that my Linux supports. Yeah, the syscall that we want is number 60, which is exit. And the way you call, like the way you make syscalls is that there's a special instruction for that, called syscall. That's it, that's the instruction. And then the operating system will look into the registers, and depending on that, do different things. So for exit, the rex register needs to be set to 60. Yeah. Here. Yeah, that's just the hexadecimal encoding of the syscall number. And then we can see that the RDI register should contain the error code. So each program in Linux exits with some code that we can actually see. So you can do, I think, echo $? To see that what's the exit code of the previous command. So hexdump, for example, returns 0, which is the default value for I executed successfully. Right, so we want to perform an exit syscall. This is a comment, so, exit. And RDI should contain the status for now, like the error code. Status, yeah, status code. Right, so these three instructions basically move some values into registers, and then they tell the operating system, hey, please do something. The operating system will then look into those registers, see, oh, there's a 60 in here, I'm supposed to exit this program, and throw away, not execute any more code of that, and free the memory and stuff like that. And it wants to exit with the status code 42. So let's try that. Yeah, compile that, run that, and now we see that there is no segmentation fault like we got up here. But instead the program just exits. And we can also look at the exit code, and it's 42. Yes. So next, what about memory? Right now we just move some constant values into registers. We can also move memory into these registers. So for example, we can move into rex what's in memory at address 1, 2, 3, 4, 5, 6, 7, 8, 9. And these brackets basically mean take what's inside, interpret that as an address, and then take what's in memory there. And this can also be used to write something into memory. So for example, you can do this and write 60 into 40 into memory at some position. Yeah, let's just try this. And well, segmentation fault again. Why does that happen? So remember that I told you that each process has its own virtual address space. It would be kind of bad if the operating system had to basically reserve lots of memory for each process. And it's often programs don't need that much memory. So instead, the operating system is just going to say, okay, if you access some of the memory at address 40000, that's fine. But if you access anything outside of that range where you just mapped some data in there, I'm just going to crash. You're going to crash. That won't succeed. So you need to ask the operating system for more memory. And you can do that with another syscall. So there's the break syscall, which I think is number 12. Yeah, here. And we can actually look at the documentation for that. It changes the size of the data segment. What does that mean? Well, there is a concept called the program break, which basically means at the beginning of your address, of your virtual address space, the process has some memory which it can access safely. For example, the instructions get loaded into there. But then after that, if you access that, that will just crash. And the break syscall basically moves that border between the valid addresses and the invalid addresses. In other words, it gives you more memory if you increment that border. Right. Yeah, so you can increment that and you can decrement that to free memory. Let's actually do that. So we want to make another syscall, this time syscall number 12, which is the break syscall. And here we need to say how much, until which address should the memory be valid. And because we want to access this, let's just say, I don't know, 2 and then 1, 2, 3, 4, 5, 6, 7, 8. Let's just have a nice round number. So I want all addresses until this value to be valid. Yeah, let's compile that. Like this. And now the program compiles again. No segmentation fault. Because now we can just access that memory here and use that. There is actually, the operating system makes sure that that memory actually corresponds to some physical RAM in our RAM chips. Okay, that's the basic, low-level stuff of how do programs even get memory, and how can they request more memory from the operating system, how can they give memory back. Nowadays there are some more advanced syscalls as well, so you would usually use mmap, which means memory map, which can do a lot of things. It can make memory executable, for example. Oh, no, there's a separate call for that, but it can basically map memory into some arbitrary addresses, not only at the beginning of the program. Okay, so we have that. We know how processes request more memory from the operating system and how they can give memory back. But of course it's kind of tedious to use memory like this, have hard-coded addresses everywhere. You could, for example, say this function should allocate its data structure at this, in this address range, and that would work. But managing this on a huge program is difficult. Especially because maybe you don't know how much memory you need upfront, so that you can't really say this program code is going to use that part of the memory, this other code is going to use this part of the memory. What you need is dynamic memory allocation. So some program part can just say, hey, I need more memory, and it can then say, okay, now I don't need that memory anymore. And some other program part can say, I need more memory, and then that same memory may be used by different parts of the program at different times. And that process is called memory management. And the way it's done in low-level languages like C and Zig is with allocators. In C that happens implicitly with malloc and free, and in Zig you need to pass those around explicitly, but basically there is some lower level machinery that tracks which parts of the memory are in use by some program code and which parts are not in use. And the parts that are in use, we will not touch them until some part of the program tells me, okay, now this memory is free again. But of course that has some overhead, because malloc needs to do some bookkeeping, and it needs to save somewhere in memory which part of the memory is free and which is in use. yeah, let's just look into how that works in C. Yeah, here we have the main function. Let's just not use any of this. And let's just say malloc. Oh, you know what? Let's actually, yeah, that's cool. Let's create a zig file. Not because I like the zig, although I do, but because you can easily like jump to definition and stuff like that. So zig is a low-level language, and it tells me something fails here. Well, that sucks. Anyways, let's import the standard library, and then in here you can say standard.mem.alloc, I think. Hang on, let me yeah, let me just copy this. Oh, it's a testing allocator. No, I want a real allocator. More code samples. Ah, yeah. Yeah, something like this, perhaps. General purpose allocator. Okay, so what we have here is an allocator, and this is not important. The important thing is that you can then create some types. And what that create does is, oh, I can't jump to definition. That's kind of sad. Hang on, I'm gonna take a break and fix this and then get back to you. Okay, I installed Zig, and now we can actually like jump into these functions. So the create function basically gets the size of the type that you give it, and then it allocates bytes. What does that do? Well, under the hood, it just it does some, here, raw alloc. It calls raw alloc. What does that do? Well, it depends on the allocator. So an allocator is really just a bunch of functions that can allocate memory and resize memory and free memory. So for our case of a general purpose allocator, you can see that it actually uses a page allocator. And a page allocator depends on the operating system that you're running on. But if it's Linux, then it's basically this. So here's the alloc function. Which performs an mmap syscall. Like, it calls this mmap function, which then at some point calls system mmap, okay, sure. System mmap, which is defined in the C library. There you have it. It's just calling some linked code. So in the end, what malloc and free do in C and Zig and so on, they really just call malloc. They really call mmap or break or whatever system calls you have to request a memory from the operating system, and then they use some part of that memory to store information about which part of the memory is given out to program code, which is not, and yeah, they kind of manage the memory for you in a very general way. Okay, so I hope like, to be honest, this section was kind of improvised, but I hope you have a general understanding of, like, you can request memory from the operating system, and what malloc and free do is they manage this memory for you. So you don't need to care about individual addresses, you just call malloc and you get some address for like memory, and then you can call free if you're done with using that, and that memory will be reused by other parts of your code when they call malloc. Cool. Now some languages have it so that you don't even need to call free. The languages detect automatically if memory is still used or not. And this is mostly the case for like languages like Java or Python, or well, these where you don't actually have access to the underlying addresses anyway. Where the language semantics themselves, you think in terms of objects and values and so on, and not in like, you don't think about memory in these languages. And that's what we're gonna do for breakfast as well. So we're gonna have automatic memory management. So you can just use values all over the place, and the language will take care of requesting memory for that and freeing memory at the end. And yeah, the allocating is actually not the difficult part. We do that right now. So hang on, in our case, we have this test file. And yeah, like we can do stuff in here. We can create lists containing some fields, and we can compare numbers and so on. And for example, when you create a list, we actually allocate memory for you. Here's the, oh, this is not the generated C code. Let's actually run our compiler. Yeah. So our compiler took this code right here and compiled that into a C program, which you can see here. And in here, we actually have lots of calls to malloc. So, for example, to create an integer, we actually allocate memory for that integer. And then we use that. And for integers, it's kind of overkill. You don't need to, like, you could just save them right in here. That's like another topic in itself, like stack versus heap memory. We're not gonna go into that right now, but instead, yeah, we allocate memory for the integer, and then we use that. But we never free any memory. So that's what we want. We want to basically insert free calls in our code. Yeah, let's maybe create a program that actually like does some interesting things. Oh wait, I could just use our extension to get syntax highlighting. Well, yeah. Is there like close folder? Close folder. Oh, yeah. Here is our code. And let's maybe create a number and another number and yet another number, and then put those into a list. So here we have a list of A, B, and C. And then, you know what, let's actually do that inside of a function. Like we have a function, foo, that takes an item, why not, which is an int, and it returns a list of int. What it does is it creates, yeah, let's just say it creates a list of the item and do int 3. here. L is list that contains 1, 2, and 3. Oh, you know what? Let's actually let's get an item from a list. So we have this list of item and 2 and 3, and then we get the item at index 1, and this results in this 2 to be returned. Right now, if we call this, this should type check, I think. We will allocate memory for the list and put items in there. Cast from never to int. What is going on here? Building crash out of bounds. Okay, true. Yeah, we don't... okay, some of the casts don't actually work right now. Do we want to fix that now? Yeah, let's fix that. Cast, compiling cast from never to something. Yeah, to do. Yeah. In here we just, I think we can just return the parameter. Yeah. It doesn't like match the type, but maybe it works. Okay, so we can compile this program to C, and now we can compile that C program. Yeah, we get a warning, sure. And we can see that this works. So it created a list of 1 and 2 and 3, and then it gets the item at position 1, which is like 0, 1, it's this 2, and the last expression in this function is returned, so this function returns the 2 as an int, and that means that the main function returns 2. But if we look at the generated C code, not in here apparently, but in here, we see that we allocate memory for a list. Yeah, here's the main function. We call this, hang on, word code test.c. Oh yeah, this is not the newest version. I was kind of confused because the code did what it was supposed to do. Okay, so in the main function, we call foo, and foo allocates memory for, the 2 and the 3, and then for a list. And it calls this list creation function with the 1 and the 2 and the 3. And then it gets an item from the list. But then the list isn't actually in use. So we need to somehow free that list here. What we really want is something like this. I don't know, free this list, free this. But of course, we don't just want to free this list, because this actually, this is a linked list. So the list actually contains the next node of the list right here. And that again contains another node. So we want to free all of them recursively. And yeah, that's kind of difficult. We need to know which of these allocated objects we need to free and which we don't want to free. Because, for example, we also want to free the memory for the 1 and the 3, because they are not used by our program anymore, they are inaccessible. But we don't want to free the memory for the 2. Here we create the number 3, And after we return from this function, there was no way to get to that 3 anymore. We created a list containing that, and then we got something out of the list again. But the list can never be accessed by any code down here. When we are here, we want the list to no longer exist, and the 3 as well. And actually the 1 as well, maybe? Yeah. So how do we do that? And there are basically 2 techniques that languages with automatic memory management use. And I'll explain them with some drawings. Okay, so one of the techniques is it's called tracing garbage collection, and the other one is called reference counting. Okay, so how do these approaches work? Tracing garbage collection and reference counting. Let's have a small scenario. Let's say, very similar to what we did in our code, we create a list. Create list. We call that, I don't know, L, and it contains the items 1, 2, and 3. And then we get the center item, that's the 2. So list get item at index 1. And yeah, then, basically we return 2, or like, basically the variable L is no longer accessible here. The only thing that remains is the 2 variable. So how does that work? Basically, first we create, we have this list of which variables exist. And this is also called a stack. So first we create a variable for the list, and that's the list, and that points to somewhere in memory where the list actually lives. So there is some object in memory that represents the list, and it will contain other objects. It will contain the 1, it will contain the rest of the list, which is actually another object, which then contains the 2, and contains yet another object, which is the rest of the list, which contains the 3, and contains an empty thing. Yeah, this is how the list looks. And then we get the first item from the list and assign that to 2. So now 2 will actually point to this value right here. And the question is, if we return 2, so basically list goes out of scope. How do we find out which objects to remove, which memory to free? And the first approach to this is tracing garbage collection. It basically means that, that you go through all of the variables that are defined, and you mark objects as reachable when they are pointed to. So for each object, there is like a separate space in memory, just reserved to marking an object as being reachable or not reachable. And initially, like let's say we are still inside of the function. Yeah, we're still inside of the function, and the list variable still exists. Like this. Now we might decide to go through all of the variables. Like the order doesn't really matter, but for illustration purposes, let's say we go from the most recent variables to the variables that were defined before, and we look at that variable, 2 in this case, and we just follow that reference. We see, okay, it points to this object. So then we mark this object as reachable. Okay. And then we look at the next variable, and we follow that object, we follow the pointer, and we mark that object as reachable. And whenever we have an object that references other objects, we follow those references as well. So here we mark that one as reachable, and we follow this down here, we follow this as reachable. So then we follow this here, and the 2 is already reachable, so we don't need to do anything there. But we also have this reference, which marks this object as reachable, which then marks this as reachable, which marks this as reachable. So yeah, all of the objects are reachable, which is the boring case. The interesting case is when it's no longer happening. So let's say list is, we return from the function, and the list variable right here is no longer accessible. So we only have the 2 variable. Then we follow that reference, mark the 2 as reachable, and that's it. And after we've done this marking of like reachable objects, we basically go over all of the objects and free objects that were not marked before. So this garbage collection technique actually has 2 phases. There's the mark phase, which just marks object as reachable or not reachable. And then there is the freeing phase, also called the sweep stage. So this is called mark and sweep garbage collection. Right, so in this case we would basically free this object and this and this and this and this and this, and only retain the 2, which is exactly what we want. Now, there are some downsides with this approach. The main downside being that in order for this to work, you basically need to stop the program at some point, go over all of the variables that are defined, and do this expensive marking and sweeping. And the problem is not that these operations are expensive, but that you need to stop the program at unpredictable times. So this means that, for like latency sensitive programs, that basically doesn't work. You can't just be expected to, at any time your program could be stopped, and then it takes, I don't know how many, even if it's just a few milliseconds, it can be a long time in some games, for example. So everything is stopped, analyzed, and then your program continues. That works in some cases, but it's also not optimal in others. So the other approach is not to stop the program at all. And instead, we track for each object how many references are there to this object. And this is not something that happens once, but you need to keep those references up to date all the time. So for each operation that you do, you adjust the references accordingly. Yeah, this is actually this is something that happens over time. So let's remove this and see how the program evolves over time. So first we create a list called L. And called L. And what that is, it's a list with two values, a 1 and another list. And like while we are creating these values, first we actually create only the 1, and we know there was one. When we put that into the list, we know there was one reference to this 1. And yeah, there's another list which contains the 2, and yet another list, and this contains the 3 and the empty list. So basically, while you are creating these data structures, you save for each object how many references, like how many incoming references are there. Here there's one reference, here it's one reference, here it's one reference, here's one reference, 1 and 1. Pretty simple. And then you keep those up to date. So in here, when we say we want to get the first item from the list and save that into a variable, actually what we're doing is we create a new variable which points to this 2. But when we do that, we also update the reference count. So we change this 1 to 2. And then when a variable goes out of scope, we decrement the reference count. So here that 1 turns to a 0. Basically, when you create a reference to something, whether through a variable or some other object, you increase the reference count. And if the variable goes out of scope, you decrease the reference count. And in this case, the reference count is actually 0 now. And that means we can free that object and also decrease the reference counts of the referenced objects. So this now has a reference count of 0, and this object here as well. Which means that this is freed and this is freed. Oh, that means that we need to decrease the reference count of the referenced objects. So now, and I think you can see where this is going. This now has a reference count of 1, and this down here a reference count of 0. The 1, we retain that, but that reference count of 0 means that this is freed. And yeah, similar, like this becomes 0 is freed, this becomes 0 is freed. So we end up with the same structure of objects, only the 2 remains. Yeah, often there's it's a trade-off. There is none of these two approaches is perfect. The approach where we stop the program and analyze the objects, the benefit of that is that we don't need to do this extra work of updating references and like incrementing them, decrementing them. That takes some time. Like all of the operations, like even just getting an item from a list, they get more expensive with reference counting, because now we need to increase the reference count of an object. In the other approach, like tracing garbage collection, we would just get a reference to that object and we're done. So it's a trade-off between throughput and latency. In the tracing garbage collection, that was, well, of course, that doesn't work. Should have used layers more carefully. Well, in the tracing garbage collection, the throughput is greater because you can just let your program run, maybe for an hour or something, as long as it doesn't use too much memory. And then only when it uses too much memory, you just stop it at one point, collect all the garbage, and then you can leave it running again. But if you only do that like a few times if you don't do that often, that's nice. Whereas the reference count slows you down all the time. But of course, there is no garbage collection pause, so the performance is more predictable. Yeah, another downside that I should mention of reference counting is that it doesn't work in some cases. So for example, let's say we have some object and another object. And this object points to this object, and this object points to this one. And you can easily do this in Java or something. In that case, the reference count of this will be 1, and the reference count of this will also be 1. So a reference counting garbage collector would never detect these cycles in the object graph. Whereas the mark and sweep algorithm would just, it would just go through the variables, mark these objects as reachable maybe, and these objects, they never get marked, so they get removed as well. The thing is, in our language, breakfast, we don't have object cycles. Our data is immutable. Like, once you create a value, you can never change that. Because it's a functional language. Once our list append function, for example, it will take a list and an item, and then return you a new list. The original list will never be modified. Once created, objects never change. And that means that, assume you can basically order your objects on like a timeline. First we create this object, then we create this one, then this one, then this one, this one and this one. And when objects are created, they can only reference objects that were created before that. Of course, you can't reference objects that are, that exist in the future. And that means that there can be no cycles in our objects. So I hope you see where I'm going with this. We will probably implement reference counting for breakfast, not tracing garbage collection. The program performance is a lot more predictable, although there is some overhead of reference counting. But yeah, I think that's the right trade-off for our case. Okay, so we have done that. Now let's actually implement that. Yeah. Here's my code. So what do we want to do? We need to save reference counts. For each object, we want to save how many references are there to this object. And that means that each of these structs that we have actually needs to contain an additional variable, like reference count. Let's just call it RC, because we have a lot of these variables, and yeah, RC is fine. Yeah, so each struct, no matter what it is, contains RC. And then we need to update them at some point. Okay, I don't want to save the changes I made here, because of course we want to do that generally. We want to do that in here. This is the code that compiles our typed program representation to C code. And yeah, we have the types in here, and you can see that depending on what kind of type it is, we do something different. So for example, our int will be converted to a struct that has the value. A string will be converted to a struct that contains the data and the length. An enum will be converted to a struct that contains a tag and a union. Basically what we want now, I think, is to just have each struct also contain a reference count. Let's compile that. Yeah. Okay. Oh yeah, let's look at the C code. No, I haven't. Don't save. Yeah, this is the updated one. Yeah, and each type in here has a reference count inside. And that's pretty neat. Now the only thing we need to do is allocate memory for those. Increase and decrease the reference count as we interact with the object. So right here, when we malloc an object, we have a single reference count for that. The reference count should be 1. So let's do that. Let's see, here we have the function implementations, and we compile the individual, the function body. We compile the function body, which we do down here. So we malloc an object, and after that we want to set its reference count to 1. The reference count should be 1. Okay. Seems fine. Oh, except this will mess up the indentation, so let's copy this thing down here. I kind of hate it, but okay. So the reference count is initially 1. And now we need to think about how do these, operations affect the reference count. If something is known at compile time, yeah, it's fine that the reference count is 1. That's cool. If something is the result of a switch, I don't even know. Like the reference count may be, Oh, okay. So I think the operations can be a bit more expensive. We don't just need to increment and decrement the reference count, but also when we do stuff like, I don't know, in here we switch on something, and oh yeah, let's assume we have some value like this 2. I think I see where this is going. When we switch on that, we basically have these parameters here. And these parameters mean that now there's a separate reference to that. Let's look at an example. With a switch. Yeah, here. So if we have a list of ints, and we call getMaybe with an index, we basically switch on the list, and we get a reference to the we get an additional reference to one of the items. So if the list is more, then if we basically compare, is our index 0, and if so, then we return. I hope this is something that we return. Yeah, we allocate that here, and then assign that to 14 here, and then we return that. We return the casted part of this list item. And here the reference count of that list item should be increased by 1. So basically here we should say, I don't know, dot rc plus equals 1, something like this. Yeah. And even before that, like switch 6.tag. Oh yeah, here we create a new variable which references, some internal part of that. That means that there is now one more reference to this object right here, to the payload. So here we would also need to increase the reference count of the payload. Yeah, let's do that. So what do we do here? We declare that, okay. Assign that payload. What do we do here? And then we also want to increase the reference count of that. So it's param.item rc, we increase the reference count. Nice. Yeah. Then we compile the switch branch. Okay, cool. So basically each time a new variable comes into scope, we want to increase the reference count. Either it comes into scope or it's referenced by another object. For a tag, something similar will happen. So here we have the variant. Yeah. And that we set the tag of that variant, sure. And then we set the payloads. And that means there are additional references to the, to the arguments that were given to the tag. arg.item.mangle rc is increased. Okay, and then for calls, do we need to do something for calls? Yeah, I think for calls, we need to also, we create an additional reference to the argument. If we create a local variable, I don't know, 3, and then we pass that 3 as an argument to a function, now there exist 2 references to that 3 object. First our variable, and then the function parameter inside of the function. So, what do we do here? Oh yeah, we do the actual call, I see. Types to push. I guess. Yeah, this is the actual call. But where do we need archetypes? We don't need that. What is this code? Yeah, let's remove that. Right, so a call just becomes a single call, which is fine. But before that, we also want to increase the reference count of all arguments. So print some indentation for that, and then write the argument reference count gets increased by 1. Cool. For instructions, I'm not actually sure. Let's worry about that later. I think the reference count of 1, it kind of only matters for some of these. Like for comp time values, the reference count should be 1. But for switch, the reference count will we just assign something to that generated ID. So we don't actually need that specific reference count. For the tag, the reference count should be 1 as well. Like this. Where does ID come from again? Okay, yeah, should be ID.mangle. Oh yeah, no, this doesn't make any sense. Okay, for calls, we increase the reference count. For instructions, we basically set the reference count to 1, I think. Yeah. For concatenating strings, well, that's not implemented yet. Okay, yeah, let's just try that out and see how the code looks. Okay, there were some errors here. Oh, yeah, there was some type stuff. Expression.type. Yeah, that makes sense. This does not make sense. This should be id.mangle. Okay, but that's it. Okay. It seems like there was some additional indentation here, which, yeah, I guess let's not do that. Okay. Ooh. Yeah, making this beautiful is not necessary, but it simplifies debugging and the rest of this, you know. Okay. Yeah. Yeah, so let's maybe look at get maybe. Sure. So here we get an object, which is this complicated enum, and we get an int. Sure. And then what we do is we switch on that thing. If it's empty, then we create a none thing with the reference count 1. That's correct. And then we cast that to a none sum of int. Also reference count 1. Correct. Yeah. Why is that? Well, I don't know exactly what's going on here, but it seems correct. Okay. Yeah. And then we break. Okay, so basically in the end, the 14 right here, this has a reference count of 1. Oh yeah, and this is not actually needed. I'm just wondering, why does that even... Yeah, well, okay. Oh, so we need to decrease reference counts. We don't do that right now, I think. Yeah, as soon as a variable goes out of scope, we need to decrease the reference count. So basically, down here, we would also have to do like minus equals 1. And of course, then we also need to check if the reference count is 0, now free yourself and decrease the reference counts of the other objects that you reference. Okay, if it's a more thing, we get the payloads right here. 0 as more.0, and because we now have an additional pointer to that int, we increase the int's reference count. Beautiful. Here we have an empty of blah blah blah, the other payload, and we increase the reference count of that. Perfect. We create a new constant int with a reference count of 1. We allocate memory for an enum. Correct. Weirdly indented, but sure. Why is this happening? 1 dot reference count. Oh, the int that we have here. Oh, I think I know what's going on. Yeah, here we compare two integers, 1 and 5. And in order to be able to call this equals function, we need to pass those as parameters, which means we increase their reference counts before we do that. Perfect. Then here we create another tag, I think. Where this extra indentation thing is coming from? Like for calls, okay, we shouldn't write indentation before that, but probably after that. I get that. For switches, we don't print indentation before that. Oh, but we do this. That should be fine. Kind of strange. Kind of strange. Okay. We have a switch. Yeah, a switch means that we just allocated memory for that, printed indentation, and then we're going to print more indentation. Nope. Oh, come on. Yeah, reload this file, don't save. Almost. Let's see. So for calls, we do this, yes, but then we don't need to do this. Yeah. Okay. So here we increase reference counts. We call something, we get something back with a reference count of 1, hopefully. Then we switch on that bool. If it's true, we want to return sum. So we create a sum thing with reference count 1, with a tag with a payload. And because we just assigned an int to the payload, we actually increase the reference count by 1. Okay, sure. Okay. Cool. Cool. Okay, cool. I like that. Actually, let's decrease the reference counts, and then let's look at what else to do. So when should the reference counts be decreased? They should be decreased either when an object goes out of scope, like if if some object gets freed, then the referenced objects should decrease their reference count. And also if a variable goes out of scope that references an object, then the object's reference count should be decreased. Which means that at the end of a body down here, we should just decrease all of the body expressions. Yeah. To C. Yeah, that seems reasonable. So let's do that. For each of the body IDs, we just created them, and now we're going to free them. So id.mangle like this. Probably needs some indentation somewhere, I don't know where. Yeah, of course we do, but right before of that. Okay, that's fine. Okay. Oh man. Oh yeah, except, true. So here we create two things. We create a none, and it has a reference count of 1. And then we create this enum, this enum with a reference count of 1. And then we decrease the reference counts of these local variables to 0. And then we basically evaluate, or we result in this 1 value. Of course, we shouldn't decrease the reference count of the thing that we return, or that we evaluate to. So basically, if the ID is body.returns, I think, then we want to continue. This call doesn't work. Yogurt ID and yogurt ID, we can't compare them. That kind of sucks. Let's change that. Yogurt ID. Up here probably. Yogurt fun, yogurt ID. Yeah, let's maybe do that here. So if we have yogurt ID A and yogurt ID B, we want to be able to compare them by just comparing their int values. Like this. They do have an int, right? Yogurt ID int, yeah. Okay. Let's look at the C code. Oh, yes. Nice. We create this expression 2. We create this expression 13, each with reference count 1. And because this body evaluates to the expression 13, only the expression with reference count 2 is, the reference count is decreased. The one of 13 stays the same. Okay, I think we have accurate reference count tracking. Of course, the thing is that we want to do complicated things depending on the reference count. Especially when we decrease the reference count, we want to check, is the reference count 0? If it is, then we also want to decrease the reference count of our referenced things. And these are type-specific operations, and they're kind of, they require some amount of code, and we don't want to do them inline. Like everywhere we decrease the reference count, we want to put the code in here. That would be a bit bloated. So instead we'll create new functions for each of the types that we have. So here these are the types. And for each type we need one function that increases the reference count and one function that decreases the reference count. Okay, we can do that. We have the types defined in here. Yeah. Okay, and then in here we have the type reference counts, or like reference count operations. Let's just call it that. And for each type in our types, we basically want to create two functions. Yeah, the functions, they don't return anything, and they will be called dupe and drop. So dupe increases the reference count by 1, drop decreases the reference count by 1. Dupe for like duplicate, or like, I want another instance of this value, and drop for like, I don't need this instance anymore. Okay, so dupe and drop. They should contain the type name somehow, so I'm just gonna put that in the function signature directly, like this. And of course they take an instance of that type, or rather a pointer to that. So they take an object, a value, or whatever. Let's call it value. Okay. Yeah, we could also print the type name in a readable way, because why not? Oh yeah, and here this is the function body. Currently it does nothing, but it should do something. Let's look at that. We have our types, our type definitions, and then, boom, reference count operations for new line. Yeah, but for int, for never, for all of these. Okay, what do we do in these? Before we think about that, let's just actually call them instead of operating on RC directly. Yeah, I think this is fine. The RC is initially set to 0, but each time we increment something, we actually instead call param.item.type. Is there something like that? Oh yeah, this. Oh. Yeah, let's factor that out. Okay, we call the dupe type with that ID. Okay. Here as well, the argument has some type, and then we call dupe on that argument with the argument. And it's not fun.get, because this is the arg item. Okay. Yeah. For calls, something very similar. No, we don't just do this, but instead we duplicate the item like this. Cool. Next, decreasing the reference count. Oh yeah, and that only happens at the end of function bodies. Cool. So this will be called drop of that type with that ID. Okay, yeah, we have dupe and drop functions for ins, for never, for false, and so on. And then down here, oh yeah, there should be some curly braces missing somewhere. For params. Wait, that's for calls, right? Yeah. That seems fine. Hang on. For switch payloads. Switch, payload, dupe, yes. There should be curly braces around this. Okay. Nice. Call dupe int. And then down here that one what's going on here? Dupe and drop. Oh wait, do we do both? No, just drop that. Oh yeah, because it's assigned here. Sure. Yeah. So you can see here we create, we want to return some int. So we get the payload of that. Ah, yeah, we have this variant, this enum with only one variant, sum. It contains an int, and we want to return an enum that is none or sum and contains the int. So we switch on the original thing, and there is only one possible thing, so there is only one branch. It can only be a sum thing. So then we get the int from inside of that, right here. And now this variable is an additional reference to that integer. So we call dupe int. And now let's assume the reference count of the int is 1 at the beginning, and the reference count, let's assume the reference count of this entire enum is 1, and the reference count of this int as well. Here we increment the reference count of the int to 2. Then we create this other int, because of course we need to cast the int to an int. And this will hopefully, yeah, it will just return the integer. Very simple. But it means that the reference count of this will be the same as the reference count of this. So oh, yeah, but here we duped that again. So now the reference count of that internal integer is 3, because there are three references to that. There's the reference from the enum, from this, _0 thing. It internally references the int. There's the reference from this one variable, and there's the reference from this 2 variable. So 3 references to that int. Okay, so we cast that. We allocate memory for the resulting enum. We set the reference count to 1, set the tag to 1, which is the sum variant. We set the payload of that to our int right here, which has a reference count of 3. Perfect. And then we dupe the reference count again. Sure. Oh, I see. Yeah, we need to drop the reference count of the body arguments as well. Yeah. Let's just copy this. And body.params, is it called? Param ID? I don't know. Params seems fine. Yeah, okay. Ooh. What's going on here? Oh yeah, the type needs to be mangled, of course it needs to be. Okay. Yeah, that's better. So yeah, here the reference count of the int is 3. Then we increment that again, because now there are 4 references to that int. There is the _0 variable, which contains the int. There is the _1 variable, which points to the int. There's the _2 variable, which points to the int. And now the 3 variable internally also points to the int. 4 references. And then the 1 and 2 variables, they go out of scope here. So we decrement the reference count by 2, so that the reference count is 2 now. We assign that to this value 4. And then this original thing goes out of scope, this _0 thing. So we decrement the reference count of that. And by the way, this should also free this object. But it should keep the int, because the int had a reference count of 2. So down here, the reference count of the int should be 1, and the reference count of this surrounding enum should be 0, and it should be freed. Yeah, and the reference count of the int is 1 because now we have this new enum, expression number 4, which contains the int. So basically the ownership got, like, if you think of it as terms of we create new references to this internal int, we drop the surrounding enum and free the memory for that, but the int itself is still kept around because by now it's been moved into a new enum variant. Okay, that's cool. Yeah, now we actually need to do stuff inside of the dupe and drop functions. But before that, there were some other errors where the type did not get mangled. Mangle. Yeah. Oops. Okay. Okay, so this C code should have no errors at least. Perfect. And now let's implement duping and dropping values, the reference count operations. Right, so duping values. This is the easy one. Basically, we just want to increase the reference count. So value RC plus equals 1. And there is nothing else we need to do. Drop is more interesting. First of all, we decrement the reference count by 1. So RC minus equals 1. But then if the reference count is 0, so if value RC equals 0, we want to do some other stuff. Yeah. And what we want to do inside depends on the type of the value, actually. So this will be similar to what we did up here, where we switch on the type extend one level, true. I would have missed that if I hadn't planned on copying this code up here. Oh yeah, this is like, this is not this is unreachable by design. Okay. So depending on the type, if it's a primitive type, like an int or a string, we don't need to do anything. Boom. Nice. And then if it's a never, we don't need to do anything as well. If it's an enum, we actually need to switch on the enum, and depending on the variant, we need to drop all of the payloads. And after all of that happened, regardless of what kind of type it was, we need to free the memory. So here we have value, like free value, right? Yeah. Okay, so if it's an enum, we want to, what do we want to do? We want to switch on the tag. And for each variant, we want to print, case variant dot enumerate. If we are at this index, then now we want to free all of the payloads. Yeah. And then we want to break. Like this, and not like this. Oh yeah, we could, sure, let's variant index, true. Oh yeah, let's maybe print a comment of the variant key. Variant.item.key, right? And then for the variant, the actual value of the variant, which is a list of arguments, we want to damn, the indentation is getting crazy. Free that variant, drop that. So arg dot, it's a type, right? Or is that another map? Oh, it's enumerated. So it has an item, which is the type, I think. And it's a value as, and the key dot arg index. Bro. And then we break. Okay. This is not super readable. I realize that, but you know, this meta code generation thing is kind of what you get. Oh, okay. Oh yeah, here should be a new line. But is it correct? So we can duplicate an int that just increases the reference count. If we drop an int, then we decrement the reference count. And if the reference count is 0, then we also free the memory of that int. Nice. Similar for never, similar for this thing. Oh yeah, break doesn't have, we don't need this. Just do a break and we're good. Yeah, if we drop the value false, we decrement the reference count, and then if the reference count is 0, we switch on the tag. Oh, there is so much. Okay. We switch on the tag. If the tag, like the only possible option is that this is a false variant and we do nothing. And then we free the memory of that false thing. Let's look at an interesting part. Like here, we have a maybe. I see an ID needs to be mangled. Like, not really. Just need to do this. Okay, so we have a maybe, an enum that is either none or it's some int. Duping, sure, increasing reference count. Dropping is interesting. We decrement the reference count, and then we switch on our... Yeah, if the reference count is 0, we need to free this value, but you also switch on the tag. And if this is something, then we drop the int. And again, drop then decrements the reference count of the int, and if that is 0, it like recursively asks its children to drop things again, and so on. That's pretty cool. Okay. True. Call drop of the mangled type, please. Like, I think this is the coolest method of the drop methods. Dropping a recursive list. We decrement the reference count, and if it's 0, then we... If this is an empty list, we just, we're done. We just free this list. Otherwise, we drop the int that this list contains, and we recursively drop the list that we contain. Damn. Very, very cool. Okay, so we have dupe and drop, and they are called. That's amazing. Actually, it's kind of weird that the mallocs are like sprinkled across our program and the corresponding free calls are up here. So let's also create a function like create or make type or something like that, which will basically just be a wrapper around malloc, but it will make things a bit more like self-contained. All of the memory management stuff is in these self-contained simple functions, and yeah. So this will return a pointer to that. And what it will do is basically what until now we did in here. Malloc memory for that. Yeah. So, yeah, let's not call it malloc, let's call it make. Make this type, like create an instance of this, or like new, we could call it new. New int, new something, and it just mallocs memory for that. And yeah, that's it. And the type is not needed here. Cool, cool. So now down here we can call new instead of malloc, and it will immediately have the correct, there's not a huge difference in what actually happens. It's just a bit cleaner, I think. Yeah. Okay. So our actual code is really, really readable. Okay, let's not get too carried away. Of course, it's horrible, but we have like new type int, dupe type int, drop type int, and so on. Yeah. Actually, let's see if built-ins work correctly. Yeah, they do. They take 2 arguments, like this subtraction, for example, and it creates a new int. Oh, this could also be inside of that. Let's do that, yeah. Setting the reference count to 1. That's kind of important, so we don't need to do that. Oh, wait a minute. This is not... If we have some sort of switch, yeah, here. We assign to that the result of some other call. We don't need to create a new object for that. So really this should be separate. We should just say, this is not initialized. It's just a new expression. And then when we actually create a comp time value, that is when we assign to that, a new value, like this. Yeah, okay. Cool. And then, do we do that somewhere else? Yeah, I think in here for the tag. I don't know if it's a comp time tag. Yeah, we need to allocate memory for that, of course we do. So this, oh yeah, we do that up here. Okay. Yeah, this is very similar. When we create a runtime tag, like, hang on. We also need to create a new object for that, a new value. And we don't need this because this will, we will put this into the new function itself. A similar thing here. We'll just new and then the type. Hope, kind of like this. Yeah. And then the new call is up here. It doesn't just do this, but it also sets the reference count to 1. Okay, so it creates a new variable called value, which is malloced. It sets the value's reference count to 1, and then it returns that value. And there should be new lines here. Okay. Yeah. This no longer, like this is not initialized. That's super cool. And only when we actually create new values, we allocate memory for that and set the reference count to 1. Cool, I'm happy with this. Let's actually see if this compiles. Okay, perfect. You know what I want to do? I want to print some debug messages in here. So we can see that memory is actually, like at least for the new and the freeing in here. We could, the code would be kind of cleaner if we have a separate function for freeing, actually. Yeah, let's do that. Even more functions. Let's say we have free this value, which doesn't do this, but it just immediately, with less indentation, it can free that value. Yeah, and this drop up here just does, if the reference count is 0, then we call that free function that we defined below, which then, frees the value, and that's it. Cool. Cool. Too few arguments. Oh yeah, with the value. Nice. So we can create a new false instance, allocating memory for that, setting the reference count to 1, and then we can increase the reference count and we can decrease it, and if it's 0, then we free that false, which means that we free its children, there aren't any, and then we free the false itself. Beautiful. Okay, so creating a new thing and freeing, I want to create logging for that, just for, like, for fun. New type, I think. Yeah. And types don't contain quotes, I hope. Oh, not a new line in here, but we want to emit a backslash and then an n. Oh, the meta level. Yeah, something very similar happens here. Oh. Reprint free that value. Well, free that type. Okay. Oh, okay. What's going on here? This seems correct to me. Yeah, we should have new lines, but apart from that, what's the hang up? If there's a declaration of function free type something. Really? Why though? Let's just recompile this. Shouldn't do anything, but okay, let's look at the first instance maybe. 174. Free type int. Oh, Oh yeah, because it's only defined below that. Sure. Let's reorder these. No, that doesn't. The types themselves can also be recursive. So I think we actually need to declare those functions similar to how we do that with the yogurt funds. Yeah. Oh man. So first declare all of the functions and then use them. Okay. Yeah, not this, but yeah, basically do this. We want a function that, new, that creates a new type. We want a function, and then we can actually reorder these a bit. Do we? No, that's fine. Okay, we have new. We have dupe of that type that returns a void, but it does take this as an argument. There is drop and there is free. Ooh. Okay. Yeah. Oh man. So yeah, we have functions new type int, dupe type int, drop type int, free type int. Seems correct. And that for every type. And then the functions are actually defined down here. And they print when things are allocated or freed. So let's actually look at that. Oh, what? Okay. Damn. Okay, let's maybe look at... I'm so excited. Oh, that doesn't... What does this do? What does this... Oh, yeah, it's not saved. Yeah, probably. Yeah, it's just this. Okay. So we call the foo function. Okay. Can we look at this side by side? Probably. Yeah. Hang on. I want to put that there. Nope. Not quite. There. Yeah. And I want this code. Okay, so we create a new int, the one down here. And then we call foo, which means, it wants to call the list function with the item, sure, and these other int constants. So it first creates a new int and another new int. Boom. Yeah, so it has created all of the arguments. Then it calls the list function. List function with 3 items is defined as this right here. So it calls this other list function with 2 items, and that calls this list function with 1 item, and that just creates this tag. So it creates a new empty tag, this right here, and then it creates a new tag of the type more and int. More int empty. This. Fantastic. And then the cool thing is it casts this tag to a list, which is a more general type than just, it also has the empty variant. So it casts it to this right here. So far, so good. Yeah. It does kind of worry me that there are 2. Oh no, that makes sense. Because in order to cast this to the list, it actually converts the empty thing to this type. So it has one instance of this type that's just empty, and then it has another instance of that type, which is this surrounding tag, more. And then can free the original specific types, like the enum only containing more and the enum only containing empty. And then in the surrounding list function, we again create this more tag with a type more int and a list. And we want to convert that to a list as well. So we convert that to this list and then free the original thing. And similarly for the list of 3 elements. Okay, now we've created a list of 3 items. And now we call the get function on that. That means we create a new int, the 1, correct? Here, what does get do? It basically takes the list and that calls get maybe. What does get maybe do? Well, it looks at the list. This is more. Like the list is not empty. So it looks, it checks if the index is 0. So first it creates a new int, the 0. And then it calls equals, which, returns less or equal or greater. Correct. Hang on, equals, what does equal do? Somewhere down, up here. Yeah, equals int. Yeah, that compares the ints, that creates less or equal or greater. And then it creates this false thing, casts that to a bool and discards the original false value, and then frees the original less or equal or greater value. Fair enough. Yeah. So now we know that that this index equals 0. Phew. Okay. Which means, sorry, it doesn't equal 0. So on the rest of the list, we call get maybe again. Okay, which basically does the same thing, and that again does the same thing, except this time hang on. Yeah, when we create this less or equal or greater, it's actually equal. So then we create the true variant, convert that to a bool, and then down here, we switch on that true and create this sum of the original int. Then we return from the function, which means that the 0 that we allocated here can be freed, as well as the bool. And then from the surrounding call, we also free the 0 and bools and so on. Okay, sure. And then at some point in here, we want to call unwrap, so we create a new string. Crazy. And unwrap, it matches on that enum and returns the string. So it takes the, so it frees the original, it returns the contained int. So it just contains the, it frees the original maybe thing and the error message string. And then we free all of the list. Whoa, because now the list is no longer, the list no longer exists. At this point, we return from this function and the list goes out of scope that we created here. And we only have the reference to the one item inside here. So we free the list, which again then recursively frees the rest of the list, which again recursively frees the last item of the list, which, by the way, also frees the integer. And, some of these free integers as well, the other integers that were in the list. and as well as this get1 integer. So I think these are the list contains 3 integers. These are the inner nodes of the list with the 1 and 3, which are freed. And this is the integer back here. And then we only have the remaining result. Damn. Okay, so obviously, like if you know C programming, you will like this is not good. Memory allocation is typically considered quite expensive, and the fact that we allocate every single int and string and enum and the false literal, we allocate that on the heap to then convert this into a bool and then free the original false. Like that's super, super, super inefficient. But I mean, we can optimize that later. I'm not going to do that right now. When we optimize that, it also makes sense to have probably a separate compiler stage, which is just, which calculates more efficient memory layouts for all of these values, which basically manages, like, it decides which values will go on the stack, which will go on the heap. It will unify some of the dupe and drop calls and make it so that objects are freed earlier. So for example, this 1 right here, it doesn't, like this, this 0 right here, it can already be freed once we did this call and we now have a bool, because the 0, we don't need to keep this int around until the end of the function. Yeah, we can do like lots of optimizations in that regard. For now though, I'm just happy that garbage collection works at all. And yeah, I think I'm gonna stop it there for now and maybe code a bit more this afternoon. So see you then. I'm back. Righto, memory management works. I guess the next thing would be to actually use that. So let me adjust this a little bit. Oh yeah, there were a few things that I remembered would be nice doing. First of all, just commenting out the print things again. I'll just comment them out so we can, later, if we need them at some point, we can easily add them back. Okay. And then also, because the malloc calls are all generated here, it's also pretty easy to catch the case when malloc fails. That can happen, and I'm not sure what malloc returns, probably 0, I think. Yeah. Of course, if size, if size is 0, then the 0 pointer is returned. That's fine. What if that fails? Ah yeah. On failure returns a null pointer. Okay, so we can just check, if the value is 0. I think there's a null pointer constant in C. Not sure. Let's do it like this. Yeah, then we basically just want to crash. Or like print something probably. Yeah, just print to standard error. We do it like this, I think. fprintf to standard error. Out of memory. Right. And yeah. exit with a non-zero status code to indicate something went wrong. Okay, yeah, let's just make sure this compiles. Okay, and look at, try to compile the C code. Okay, same warning, that's fine. Yeah, allocating a new int now calls malloc, and if that returns 0, then we print out of memory. And let's just check. Yeah, first it accepts where to write that. Write formatted output to stream, so to standard error in our case, and then the string out of memory. Sure. Okay, that's fine. Nice. Also, let's do something. Yeah, I don't know. What shall we do next? I think strings don't work yet. Like, yeah, you can have string constants in your code. Like, I think you can do hello. Like, d equals hello. I think you can do that, but it doesn't do anything. Main calls our real main. Okay, so it creates a string actually. Oh yeah, and we don't need to allocate memory for that because the string is directly a C constant string. So it's, you know, somewhere in our initial program memory there is this string, and we don't need to free that. Okay. Oh, what if we combine strings? What if we say hello plus world? Does that work? Unknown reference name plus. Oh right, yeah. Of course. The prefix notation. Okay, that actually works. Interesting. What does it do though? Yeah. Oh, hello world. Well, that's nice. And then we join those strings by calling concat. Sure. Okay. I mean, yeah, this works. But what if the string is not known at compile time? What if we have a list of strings? You know, hello, or like foo and bar. I'm so creative. And then from that list, yeah, we get some item. Oh yeah, and then we calculate hello and that string. So now this string is not compile time known because it depends on a value that's only known at runtime. Okay, it compiles to C code. Wait, let's just look in here, I guess. Case concat strings. What happens here? An instruction builds strings. Okay. And oh yeah, to do implement concat. Okay, that makes sense. That's what I thought. Okay, so actually strings need to be heap allocated as well. We need to fix how we deal with strings. To do, yeah, implement concat. This is what we still need to do. Okay, how do we do that? Basically here we allocated a new string. That makes sense. And now we need to allocate ID. Hang on. What does a string have again? New type string returns a string. It returns. Oh yeah, it has data and len. Data and len. Okay. So data is something, and len is also something. Right. Data should be the joined version of strings, so we need to allocate memory for that actually. Yeah. And then the len is, the len we can do. The len is just args get 0 mango.len, arrow len plus args get 1.mango.len. So the resulting string is, basically adds the lengths of the original strings. Okay. Cool. The data. Well, I see. We need to allocate new. Yeah, let's first assign length and then allocate the data based on that length. So here we basically need to do a new call to malloc. With our new length. Yes. And then we copy our strings to that somehow. Oh yeah, we can make sure that it doesn't fail. Okay, let's write an out of memory function that just crashes. We'll do that later. And now we want to basically copy the memory there. I know there's a string copy in C. Yeah. Let's use this. Destination and source. But the problem is, C expects strings to be null terminated. And we don't do that. I think, no, we don't do that. Because that makes taking substrings and so on really difficult. So what do we do instead? Let's... How do we take substrings? Yeah, we can do memcopy, I think, which for now is fine. Yeah, destination, source, and count. That's perfect. Memcopy. Memcopy destination is our string data. We want to copy the first string to that. So args get 0. Data. Yeah. And how much do we want to copy? Well, basically the length of the first string. And then we want to do that same thing with the second string. But of course we don't want to copy that to data, but we want to copy that to data plus whatever is the length of the first string. And we want to copy the data from the second string with the data with the length of the second string. Yeah, that makes sense, I think. Ooh, yes. Yes, okay. Yeah, I should... don't like that. I should print annotation for this. Not beautiful. Not beautiful at all. Well, okay. We can concatenate strings, kind of, I guess. Yeah. Let's look at the C code. So here we have concat. Whoa. Okay, so it creates a string. Allocates place for string, like only for this right here. One int, a char pointer, and a size. And then it will set the length of that to the sum of the length of the arguments. Fine. It's going to allocate memory of that length that needs to work, and then it's going to copy the first string to that memory, and then it's going to copy the second string to that memory after that. Okay, then it drops the original strings, also correct. Oh wait, dropping strings doesn't actually like free the underlying thing we allocated. Nope. So here we allocate memory and we need to free that when the string is dropped. So drop. Yeah. Here. Oh. Oh yeah, freeing a string is more difficult. So for primitive types, you basically want to switch on, oh, what is it, the F? Oh, this is a string, what? How did this work again? Primitive name, oh yeah, it's actually just, if name is string, then we do some stuff. Yeah, okay, so if the name is a string, then we also want to free the data of that. So we want to do value data. Oh yeah, and we want to free that like this. I think that's it. Okay, concatenating strings. Here we drop strings, so we free the strings, and then we free the data, and then free the string thing itself. Beautiful. Okay, of course now string constants don't really work because we can't free this memory because we didn't allocate that, because it's just, basically a constant string. You are not supposed to free that, so we are actually gonna allocate memory here as well. Yeah, just to make that consistent. Okay, so in functions, when we compile a string, we actually allocate data for that. String.len, yeah. Then, if that data is 0, we are out of memory. Otherwise, we copy our string constant to that memory. So basically, copy to that data our string constant. Hope it's like this. And the length is the amount that we want to copy. Let's see. Okay, so we call main. Oh, yes. Okay, so here we allocate a new string. We allocate a buffer for the actual string value. That should work. We copy 3 bytes from this string constant into that data. And then we set the string length to 3. And now we have created our first string constant. Okay, that's fine. Now let's actually implement this out of memory function, which I think I'm just going to put right at the beginning. And it's going to be very similar to this. So here we'll just do, also call out of memory. And then, like before everything, we'll just have a function out of memory. It's gonna be like printing things and exiting the program. But yeah, that's basically it. Cool. Let's see if this actually compiles. Oh, it doesn't. Damn. Okay. Oh man. Why is mem copy and string? I'm just not gonna question that. What? The organization of the C standard library is. I don't know who understands that. Oh, cast never to string. Like, yeah, this makes sense. Custom never to int. Wait, cast never to int should return an int, right? Yeah. Oh, this just returns a never. That's not correct. Oh, yeah, because we just rely on the type of the last expression. I think the clean thing would be to actually, create an, I guess, uninitialized value here. That means in the yogurt we need an uninitialized value. I think that's like a new thing in here. Uninitialized yogurt type. Oh, sorry, breakfast type. Yeah. Okay. Cool. Okay. And when we compile the cast down here to never, yeah, what we actually do is we push something to the builder, not a switch, but an uninitialized. At 2, hang on, the yogurt ops, they already have a type, right? Or like the yogurt op is contained in a yogurt expression which has a type. Okay, so we don't need the type here. Okay, that's even easier. Which means we simplify this, and then down here we can just say uninitialized with the 2 type. And we know that this cast is actually never really called, because you can't have an instance of never. So it's fine that we just create this uninitialized variable and then return. Okay. Yeah, in the C code we don't handle that, that's correct. But that should be pretty easy, right? Show param. It's uninitialized, we just don't do anything. We do print indentation though. Okay, now we do something. Okay, so casting a never to an int takes an instance of never, which can't exist, so we know that this function is never called, you know. We create an int, leave that uninitialized. What's going on here? Oh, we return the original never type. No, that's not correct. That's not correct at all. Yogurt. Oh yeah. We return the original parameter. Nope, we want to return that. Nice. Yes, cast never to int accepts never, returns int. That's correct. And then we drop the never and return the int. Sure. Okay, now there should actually be no like warnings when we compile that. Dang. Okay. Nice. Just because it's more fun, I think the main function should actually return a string instead of an int. Oh yeah. I think we have a check in there somewhere where we basically check, never mind, that it doesn't return, that the main function does return an int, but apparently we don't. Oh. Okay, only the main function, like the generated main function is wrong. Here. So calling this main function of a program should return a string, and then we just want to print that. Yeah, let's do that. Let's just adjust this code to oh yeah. So the main function should return a string. Sure. And then we print, say, we can't, like we don't, the strings aren't null terminated. So I think it's best if we just memcopy to spam it out. I'm not sure if that's the most elegant way, but you tell me. Okay. Cool. Let's see. It doesn't print anything. We probably need to flush that somehow because it's buffered by default and I don't know what. Hang on. Print I mean, yeah, sure, we could just yeah, no, I don't want that. Dot star. What even is this magic? Crazy. Sure. Sure. So we print percent dot star s. The length is the result len, buff is the result buff. Sure. True, it's data. Ah, yeah. Expects int, but it found an int. Size t long unsigned int. Oh yeah, that makes sense. I mean, let's just cast that to an int, I guess. I actually think like size t is the more appropriate type for that. But man. Okay. Hello bar is what it says. Hang on, is that correct? Yes, it is. 1, 2. Oh, sorry, 0. 1, 2, 3. Okay. I think you can only create lists up until 3 elements, so this is what we'll do. But yeah, you can now basically just never mind. Oh, again, because we really want to emit a backslash and then an n. Okay. Hello 1. Hello 2, because now we have 2 arguments. And we can't actually provide 0, so. But that's pretty cool. We have string support. Yeah, I like that. You know what, let's commit things. That would be nice. Nope, breakfast. So we, oh yeah, we do the uninitialized thing separately, I guess, because why not? And to do that, we add this. Okay. Handle casts from never. correctly. Okay. Yeah, this, let's not do that. And then let's just support strings. I mean, we kind of do already, but well. Okay. Nice. We have strings. I think in the long term it would be nice to basically to have a separate like buffer built-in type or something. So you, for example, you can have a buffer of bytes or a buffer of bools or something, and the buffer actually like puts them in memory next to each other. And then string could actually just be a buffer of bytes, for example. Yeah. I don't quite know how to do that yet. Yeah, let's do that next. Let's do that. Actually, let's support stringifying integers. I think that's like a nice, perhaps more simple task that we need to do anyway. Oh, and I haven't, like, I still did my Halloween theme. Yeah, very cool. So we have ints somewhere. Nothing, never, bool, comparisons, hashing, which we don't really have, bytes, which we don't really have, ints. Okay, so we want to be able to turn an int to a string. And let's just call this toString, I guess. Takes an int and produces a string. Yeah. So if, and we don't have if. We don't have less than, do we? If int is less than 0, yeah. Let's do this basically. We just return the result of adding. Where's my plus? Here. The string containing the minus. With basically the int, like 0 minus the int, or the negated. Is there like a negate function? I don't think there is, but it would be useful. Negate and int, and it just returns 0 minus the int. So this will actually just be negate int. Okay. Similarly here we will negate the int and then print that, which we'll call ourselves recursively. But if that's not the case, we do this, which then does this. right. So what we do here is basically we find the largest power of 10. String find divisor or something. Int and candidate is the candidate for the divisor, return the string. So this calls toString find divisor within candidate is 1. And then this will actually check things. It will check if, assuming we take the int and we divide that with our candidate, is that less than the radix? In our case, let's just hardcode that to 10 for now. If it is less than 10, then we print like toString using divisor or something like that of wait, let's do something even simpler. Oh yeah, let's just say if it's positive, let's just print the last digit and the digits before that. What is the last digit? Well, the last digit is just the int modulo 10. Yes. And the thing before that is toString recursively called on like int divided by 10, converted to a string. Oh yes, that's nice. That is super nice. Okay, so we have that. Well, I mean, of course, this doesn't work yet, because these are numbers, and we don't, like, this is a string, this is a number. We need to convert this number to, I assume to, last digit string equals basically a chain of ifs, you know, because we can't, you can only switch on enums, at least for now. So if the last digit equals 0, oh god, this code is gonna look horrible, and then it's gonna be the string containing 0. Yeah. Otherwise, you see where this is going. If the last digit is 1, then it's going to be the string containing a 1. Otherwise, if it's 2, it's going to be the string containing a 2. If it's 3, it's going to be the string containing a 3. Oh yeah, this is like totally normal code. Hang on, something is wrong. 4, 4, 5, 5, 6, 6, 8 prints 8. Yeah, 9 prints 9, with 0 was handled above, yeah. So this is unreachable. Crash. Unreachable. Crash was defined here, right? I think it was. This is horrible code. Okay, so we have the last digit converted to a string, and now we want to print the number divided by 10 plus the last digit string. Okay. Well, this is gonna like recurse forever, because this is this may be just 0, and then we print a 0 follow and before that the 0 stringified. So we basically need to check is the int less than 10? If it is, then we don't need to print anything before that. Otherwise, we print, the int divided by 10 converted to a string. Yeah, this is definitely beautiful code, for sure. And we don't even support radixes, but we can do that later. Oh god, what have we done? But now we can probably just print, for example, hello. Okay, hang on, we have never printed hello world. We need to do that first. Last digit, no, last digit. Oh no, some of this. Oh yeah. Hang on. Like this. Okay, it actually compiled. Okay, so now we have hello world. How did I fuck that up? Wait, what? Well, this is awkward. Hello world. Okay, so some memory was overwritten, I guess. How? Why? Let's do something simple. Now we gotta debug that, but before we do that, does it still happen here? No, it doesn't. Okay. We have a successful hello world. Yay! Yay, yay, yay. So now my question is, why did that happen when we do this? Ghetto world. Why? Okay, so we have this. We allocate memory for a new string. We copy the 4 bytes from 0 in there. Sure, same for 1, same for 2. We increase the reference count of all of that. because we create a list of strings. Here, list of all these strings. And then we call the get function with that list and the index that was passed in here as a parameter. So now we have that. That gets a string from memory. Okay, sure. And now we allocate the hello world string, which seems fine to me. Some memory corruption is somewhere. Why though? Why? Okay, then here we print the result. I mean, sure. What if we print... I don't really trust this, but that will probably not be the error. But I just want to check. Let's iterate over the string manually. Okay, so it really starts with ghetto for some reason. Okay, sure. So let's, in here we call memcopy. Oh yeah, and let's use that. Main. Oh, here. Yeah. And then let's actually print the data. Then is 13, and we have the data. Okay, so here it's still hello world. Well, that's interesting. That is really interesting. Here it's hello world. Okay. Dropped values. And then it's ghetto world. Okay, so apparently something is not going great there. But 6 is not dropped. Nope. Strange. Very, very strange. Dropped 0. And then we have later. Oh, and then it's already hello world. Hang on. Dropping. Hello world dropped 0, and then it's already what? Drop type int. We decreased the reference count? I mean, sure. Dropping. Wait. G is the letter before H. No way. I think I think this somehow manages to. But how? Somehow decreases the H to a G. That's a big reference count, to be honest. What? Wait, where does... Oh, wait, where does that int come from? Does it come from never? Oh, no. Int 0. 0 comes from... was duped here, comes from the outside. Type int from down here. Oh, type int is malloc of type int. True, we should set the reference count to something. I did not think about that yet. Yeah. And we don't need the int to be accessible after this call, so we'll just leave that at 1 and then call that. Okay, for some reason now it works. I'm not sure why. But I do know that that was undefined behavior, I think. Yeah, reading uninitialized memory is undefined behavior in C. So whatever, like anything could have happened. That it doesn't seem like these two things are related, but actually they could be. Yeah, so let's maybe do that. Let's just say Okay, we can print hello world reliably, hopefully. Nice. Okay, now let's print hello world. There are arguments. So let's add. There are how many arguments? Well, a true string arguments. Now we need to add something else. Well, I mean, I guess, sure. Why not? Okay, so there is no function named less than. That's sure, we can fix that. And there's ordering somewhere. Somewhere here. Yeah, we don't have operators yet, which, like these symbols, would be nice. Yeah. Now let's just implement this for ints. Returns a bool. Basically, it just compares them. So compare A and B. If A is less, yes, then it returns true. If it's equal, returns false. If it's greater, then it returns false as well. Just like this. Okay. There was no function named crash. Huh, okay, that's... we can fix that. That fits right here, I think, with the never type, yeah. Because crash has a lot to do with never. So crash gets a message, oops, never returns, and it just calls built-in crash with your message. Cool. Never doesn't exist. Doesn't. It doesn't. That may... wait, what? Should exist. I think we special handle, like special case, some types. Oh, is it here? Int? Yeah. Oh, look at this. If it's int or string or type, we do something, but we also want to check if it's never. Never type is not in scope, so we also need to add that here. Oh, we have type never. Hang on. Oh. Right. You know, it's kind of difficult to know which type is the, like, the prefix and or what is the actual name. Okay, we have C code that compiles, and there are 1 argument. Damn. What? Oh, that actually makes sense. What? Because in here, we also, like before we even return that, we also get the thing from the list. And if we have too many arguments, then no, we can't get anything from the list. What? I did not expect that. Completely correct. Yes, 5 arguments. 6, 7, 8, 9. How about 10? Damn. Okay. So we can count the number of arguments and turn that into a string, actually. Phew, that's nice. That is pretty nice. Okay, yeah, I'm gonna take a break. and then, I don't know, we'll see what we'll do. Okay, it's pretty late, so let's not do too many things right now. Actually, let's commit this first. So what we did is basically fix undefined behavior, because of course that's what we did. There was something, I'm sorry, but I want to rename the language again. Naming is hard, okay? So breakfast is kind of a long name for a programming language. And also the BF extension is kind of taken by brainfuck. And breakfast is not really, it's difficult to come up with a logo or something, just because it's more like a concept than a concrete thing. So I thought, why not call it the Plum programming language? Plum is a nice fruit. It's really good. It's kind of juicy, nice purple color. It's short, it's not taken yet by another programming language, and it could actually stand for like programming language, I don't know, something for but for now probably programming language under maintenance or something, I don't know. Yeah. And the file extensions could just be .plum, which is simple. The logo could just be, I don't know, some picture of a plum. So it sounds kind of cozy, you know, plum. So yeah, I think that's what I'm gonna go with. And I hope this is the final decision. Okay, yeah, you know what, let's just search for breakfast right here, and oh yeah, the breakfast file should actually be named Plum, so let's do that as well. Plum, and then in all of the other files, they should import plum.nar. Okay. Well, right. Alright, the types are named breakfast type, which is kind of unfortunate. Well, but you know, Plum is shorter, so at least we get that. Plum type. Yeah. Actually, let's rename all of breakfast type to Plum type. Oh. Okay. Alright, for the package thingy in here, that should just be Plum, same here. Okay. And then there's the Plum extension. It sounds kind of cute. Okay. Yeah, let's commit that. Yeah, we don't want to commit these assembly things or the zig code. Rename breakfast Plum. Cool. Oh yeah, I should rename the repository on GitHub, but I'll do that after the stream, or the video, I think. Yeah, this, by the way, doesn't really, we don't need that. Language.km. Cool. Yeah, remove obsolete language file. What next? One option would be to do error handling. Another would be to add an array. And I think because we did some memory related things in this session, I'm actually going to look at how arrays could be implemented. So the idea is that there's a new built-in type called array, and it's like a quite fundamental type, I think. Like, you know, just like int is a primitive type, we will have array buffer, or I don't know, something as a primitive type. A difference to the other primitive types is that buffer or array, or what is going to be called, will have a type argument, and it will basically represent multiple of those values in memory next to each other. And why do I want why do I want this? Well, for strings, I was kind of thinking, how could we take the substring efficiently? And currently we just can't do that. We can't, because you know, the string kind of, if you have a reference to a string, you can't really point into some part of the string. And we can't even, like, you know, add a substring function that then returns a new string that points to the same data, because, you know, the data also needs to be reference counted separately from the actual, like, string type in that case. So I'd rather just have a more general buffer or array type or whatever that deals with that problem. Right, so how are we going to do that? The thing is, this is not really, it's primitive, but it's not a string, what's in here, you know? Oh no. And even worse, like, this can be, like, it can be recursive over that boundary. You could have, I don't know, an enum type, like a maybe of a buffer of a recursive type of that maybe. Yeah, so this really has to be part of the like type hierarchy here. Okay, buffer or array, what's the better term? Actually, do I want to have a garbage collection for that type? I'm not sure. Like for the inner data is what I'm wondering. Yeah, maybe adding that type is not a good idea yet. Yeah, I think the cool thing about such a buffer type would be that it would be like it would make use of the reference counting to be more efficient. So I imagine that, for example, you could have a set method that you give an array and an index and an item, and it returns a new array that's basically a copy, except the item and the index is different. It's the new item that you give in. That means, though, that the implementation could potentially do something like, if the reference count of this array is 1, then we're just going to mutate the item in place. Otherwise, we are really going to copy the array. And most of the time, I think this will actually allow you to kind of have like mutable types at the bottom of the, if you have some expression like list of 1 and then you call add 2, add 3, add 4, this will actually like append things or like write things into the into memory somewhere, and not actually allocate a new list every time. But in order to do that effectively, I think we need to optimize the reference counting calls. Like I think we need a separate compiler stage where these dupe and drop calls are explicit and they kind of get moved around, So for example here, rather than creating the type int with a reference count of 1 in here and then duping that, we could just immediately create that with a reference count of 2. Especially if if there are other dupe expressions somewhere in this function, we could just aggregate all of them into the initial reference count. That would be so much easier. And rather than dropping these values at the end of the function, we could actually drop them the last time where they are used, basically. Yeah, so that requires some thinking and optimization, and the entire point of buffer would be to enable these efficient memory patterns and still retain the immutable semantics that we have. But in order to do that, we really need a new compiler stage. So that's like a big challenge. So let's not do that right now, but postpone that. Okay, so what do we do instead? I think it would be nice to look into error handling actually. And currently if you have some error in your code, like should use the editor with syntax highlighting and open the correct file in there. Yeah, I'm gonna rename the folder some other time. Oh, hang on. Oh, I see why this is not working. In the VS Code extension, the package JSON refers to the plum.tm grammar, but we have this breakfast grammar, so still need to rename that. And yeah. Okay, so now why is it not working? Reload the extension. We don't have... Oh, yeah, file types should be Plum. Makes sense. Still nothing. Oh, is it only activated if there's, yeah, if there's a .bf file. It should be activated if there's a Plum file. So let's do that. Okay, and we have syntax highlighting. Nice. Well. Nope, this did not yet fix syntax highlighting. Okay, so we amend the commit. Cool. Now we have syntax highlighting and a Halloween theme. Okay, we don't. Interesting. Nah, never mind. Okay, so yeah, what I wanted to show you is if there's an error here, like we just put, I don't know, Plum in here, then this won't compile, which is exactly what we expect, but, well, yes, that's actually true. Oh, and it won't, yeah, it can't open the file because, of course, it's looking for the test.bf. Okay. Yeah, it just says expected error. Oh no, the program panicked. And that doesn't tell you anything. So we kind of want to track during parsing, where does the error occur? Yeah, which means we basically need to work our way through the entire compiler pipeline and save information about, you know, the source of something. Let's actually have like a source .mar struct, I guess, which contains the file name and the offset, the byte offset in the file, I guess. Okay, so the bacon contains the line. That's nice. It will also contain a source. And that means that Plum also needs to import source. That basically tells us where did this line come from. Oh yes. So turning something into bacon, sure. An ongoing bacon. Okay, so the ongoing bacon also needs a source. And then in here we just say the source is the bacon.source. Like this. And the initial thing doesn't actually have a source, so let's maybe create a function like invalid source. I don't know. Yeah, just creates the source where the file is invalid, and the offset is 0, I guess. Yeah, I mean init, yeah, sure. Okay. Okay, and then for each line, we basically have the start offset. basically want... Oh, this is interesting. Yeah, basically we want to increase the start offset. With the length of the line. But then also return the old start. Okay, like total offset is this. Yeah. Line start is total offset, and then total offset is total offset plus line length. Much more elegant. Okay. Oh, hang on. Line len plus 1, I guess, because the new line also is also a character. Okay. So we have the lines. We have the indentation, which exactly matches the amount of spaces at the beginning. And then we look for the child that we want. I mean, sure. Line.trim, let's actually not do that. Yeah. Okay, and then we have the line start. Okay, so here we just get the indentation of the line. That makes sense to me. Yeah. Okay, so here we look for the matching node where we want to insert that. Also makes sense. Yeah, and now I basically want to say line is line.substring indentation to line.len. But also line start. Can we just say line offset? I think that's nicer. Line offset is the is line offset plus line dot plus indentation. Cool. Okay, so we strip the leading indentation. That's what we do here. And you know what? Let's actually do this up here. Okay. Find out the indentation. And trim. And trim it. Cool. Look for the correct node where to insert this line as a child. Perfect. And here we basically want to insert the line, creating a block if an extra block if it starts with a special character. Okay, nice. So if we want an extra block, yeah, we basically say, let's create a line with the source being, oh wait, hang on. This should be a range, right? Yeah, let's make this a range. 0 to 0 for the invalid one. And here the source is line offset to line offset plus 1. Because that's exactly the part of the original source file where this character comes from. Yeah, and if there is nothing else in here, then we're done. Otherwise, the rest is gonna be well, the line without the first character, not trimmed. Let's not like trim lines too far here. And the source is the line offset plus 1 to the end offset. Kind of need that too. End offset is, let's calculate that here maybe. Cool. Oh. Nice. We could just call this offset. Yeah. Let's do it like this. Yeah, total offset. Oh, there is the dot dot plus operator, which makes a range that has this as the base and this as the length. You know, this is the kind of thing that you only create if if an operator is just a single function. I would never put something like this hard-coded into the language. But in the standard library, I mean, sure, why not? Yeah, so this is offset dot end plus 1. And then the line offset exactly is the line offset start to the line offset end. Oh, right, and the start, we basically cut the indentation from the start. Similar to how we take the substring. We have something very, very similar here. I think this was just called offset. Like range, where is it offset? It's the range. Source maybe even? No, range. Yeah. Yeah, okay, so the source, of course, let's say the source just contains a range, because why not? When we support importing multiple files, sure, let's add a file to that, but for now, let's not make things more complicated than they need to be. Hang on, we were not at the toast yet. Okay, so source is actually just source, and hang on, let's create a constructor, kind of like constructor-like thing for that. Something that just takes a range, returns a source with that range. We can actually use that down here. Okay, so source is the source of our yeah, range start to range start plus 1, and then this right here is the source from range start plus 1 to range end. Perfect. Whereas here we just have the entire range. Cool. I like that. Now each, okay, let's see if this compiles. Should. Yeah, okay. Works exactly the same. Except that now each bacon node knows where it's from, which is pretty cool. And that means that in the next compiler stage, the toast, we can also give these the toast definitions or the expressions, you know, we can kind of attribute errors to places in the code where things go wrong. So first of all, this should not return a toast. This should return a result of either a toast or, I guess, a string for now. Yeah. The last expression of the function doesn't match the return type. True, because this should be an OK of a toast and a string. Like this. Beautiful. Right. Yeah, this is like actually a panic. Like this is a programming error if the line is empty. If it's not empty. Yeah, and the definitions. Oh yeah, here instead of having this panic, we will just do something very simple. We'll do we'll return an error. Couldn't pass line. Boom. And then we can just write the offset here. So bacon dot source. Yeah. Let's add a nice print for source. So you can write the source, and that will just range dot start to range dot end. Let's use a nice Unicode thingy here. Okay. From and then the source. Okay, in the main Plum file here, this may fail. So we actually, you know, if an error occurs, we can handle that here. We just print the error and I guess we just exit. Yeah. Nice. So now, if there's an error, program panicked. Okay. Yeah, but let's do something else here. Let's make something that is not just this, but something, I don't know, this. Like that's completely invalid. Never mind, I guess. What? How is that valid? It just gets ignored. That is strange. Like really strange. Interesting. Let's maybe put a percent in there, because why not? Please tell me that doesn't work. Oh no. Yeah, we create an error, but we don't return that. Okay, so we should of course return that error from this function. Okay. So now, yes. Instead of just panicking, it tells us, hey, there was a compilation error, couldn't pass this line. And then also the offset, like 9,434, which like, obviously that's, what was a 9,400 something. Yeah, so 9,434. Kind of like here, that's weird, but okay, I mean, sure. It's at least the correct region. Nice. We have arrows that represent a location. So let's do the same for the other parsing arrows. So converting this to, so basically each time we see a panic in this file, we should instead just, return an error. So this will be a result from maybe string to string. And if we are at the end, then we want to return an error of maybe string of panic. And I think this is a very common theme, having something that returns a result of something and a string, and that something is a maybe. Because most parsing functions return, a maybe thing. So let's actually define some helper functions first. Yeah, let's define bad input. Which will just create a result of maybe t and string. With an error message. And it will create an error. So yeah, this is kind of what you get if you don't have a great type inference. Okay, so inconsistent return types, that's true. So this is also the case. Basically the parser doesn't match. Like this is no match. Doesn't need anything, it just returns this. And it returns an okay with a none. the other option is that something was parsed, and that just returns an OK with a sum. Okay, these are the three options. Either the parser doesn't match. It's like, yo, you try to parse a string, but there's no string coming here. Or it's a bad input. Like, this is definitely a string. You know, the string was started, but it never ends. Or something was successfully parsed. So this still returns, you know, this result thing, but then in here we can just say return no match. And in here, instead of this, we can just say return bad input. And down here we can say, hey, we successfully parsed a string. And here we can actually use type inference because the t, you know, it's obvious from the parameter, from the type of the parameter here. Okay, similar thing here. This will return a result. Yeah. Return. I guess return no match. And here return no match. And here we successfully parsed this thing. Yeah, there is no panic in here. Okay. Parsing a name. Can that fail? Not really. Wait, parse identifier? Oh, that can fail. But wait, there is no panic in here. Yeah, let me undo that. Because this can never fail or like result in an error. Either there's an identifier or there isn't. Yeah, so this is, yeah, just calls parse identifier. Same here. Parse atom. Yeah, this can definitely fail. So this will be a result. And instead of panicking, we just return bad input. Expected parenthesized expression. We can also like make these actual nice error messages. Here we can say return bad input, oh, by the way, of a closed expression. Expected the closing parenthesis. Cool. And then in here we successfully parsed something. And here instead of, you know, returning sum, we just return parsed expressions. Nice. Of course, parse string can also fail. So if this returns an error, we want to bubble that up. Yeah, this can't fail, this can't fail, this can't fail. Okay, what's here? Oh, probably this down here. If nothing could be parsed, this is no match. Parse unpiped expression. Also a result of that. Yeah. First we try to parse an atom, then we push an atom. These should be unwrapped, or they bubble up the errors. Okay, and down here we just say parsed expression. Beautiful. Expression is parser.parse unpiped expression, question mark, because it can fail, or we say no match. Oh yeah, right. Question mark only works in functions that return a result. If that fails, we just return this parser doesn't match. And if there is no expression, then this is a bad input. Expected expression. Ah yeah, return that with bad input of a toast expression. Finally, we have this piped call. I mean, sure. Yeah, parse expression can fail, and here we passed something. There's an error here. Okay. Oh, maybe of maybe. Because the expression, right, we need to add the question mark there. Now it's going down. Down here. To toast expression of a bacon. Do we want to give up on the first error? Yeah, I mean, yeah, for now. Yeah, let's just do that. So this just returns a string. In this case, no match. In this case, create bar. Oh, hang on. Yes, like this. Instead of panicking, we return bad input, expected expression. Beautiful. And same here, just return bad input of a toast expression. Instead of panicking, parse switch can actually fail. So this returns a result. Okay. If there is no %, this parser doesn't match. All of the panics, they instead return bad input. Okay. No. Yeah, I mean, some of these can definitely be improved, but you know, for now, I think that's fine. Okay, and then here we passed something successfully. Similar for a pipe, probably, yeah. Returns a result. Instead of none, we return no match. Instead of panic, we return bad input. In the end, we say, hey, we passed things successfully. Is it similar for a call? I'm not sure. Not really. No, passed. A piped call always works. To toast expressions, yeah, these can all fail, so this needs to return a result. And the parse switch and pipe can fail. This can fail. And here we yeah, we can't actually use parsed. So this is just an okay. Okay, Yeah, the children are probably, yeah, need to be that. There can be an error. What's here? Body is case.children toast expose question mark, because this can fail. Oh yeah, like this. Children dot empty to toast extras, yeah, because this can also fail. Oh yeah, you know, I think it's in the big picture, it's nice. Like it really was a good idea that we postponed the error handling, because it's just a lot of boilerplate most of the time, and doing this, like, now I'm just going through all of that and systematically adding things. That's fine. Like, that's totally fine. It would make no sense to do error handling right when you're writing the code. Yeah, instead of panicking, we really want to return a bad input of toast fun. Oh, by the way, same here for all these panics. We just want to return that import of a toast fun. Cool. Yeah. Or return that import of toast fun. Boom. Beautiful. And here we passed a toast fun. Noise. Yeah, this can fail. Okay. Yeah. To toast type def can't fail. That's kind of okay, because it just panics. I mean, can't argue with that. Okay. Okay. So now if there's any error, I mean, okay, this already got caught. But if we put some, you know, some more subtle error in here. Instead of this, let's say we have a 3 in here, or 2. I think that was an error before. Yeah, like before that just panicked, and now we get an error. And we still don't really have a location for that, I guess. Which is kind of unfortunate. Okay, so I think these things, they should not return strings, but they should return some sort of error. And let's maybe add error in here. So struct error has a source, yeah, and has a message, which is a string. So, you know, an error basically has a location attached to that, so that we can then later on show errors in the code, or like at least point you to the correct place in the code. And yeah, let's rename this to error, because source is really just, I guess, a helper class for error. Yeah, error feels more like the main thing in that file. Okay, so in the toast, yeah, we have a lot of these result functions now, and we'll adjust them so that they return an error. This returns an error, and this returns an error, and this returns an error. This returns an error, and this returns an error. This returns an error. Errors everywhere. Okay, and then we should get errors for each time that we call bad input, because there we just, you know, we pass in a string instead of an error. Oh, and by the way, we should also, oh, okay, these are already adjusted. No match. The last expression doesn't match because these should be errors. Beautiful. Right, right. Yeah, so this should not take a message, but an error. And now we should get errors for each time we use bad input. Yes. Yeah. Let's just say the error. We kind of need like a constructor for that. Error. It should take make error? No, I think error is fine. Yeah. Just with message and the source. Yeah. So here we have the message, and the source is bacon.source. Boom. I mean, this is not the most precise source, actually. We could do something better here, I think. Yeah, we could see what's the, basically what's the offset of the parser, and then based on that, figure out where in the string we are. You know what, let's actually do that. Huh. Yeah, let's do that. So here we return an error, expected, type thing, and then we take the bacon source start plus the parser cursor up until bacon source end. So basically the rest of the line will be the error. Expected equals sign after type signature. That's nice. Right. It only has a range. Oh, of course it does. Can we even, I think this is a common pattern. I think we'll have, I don't know, source. I basically want to, without the first n characters. We could just do without first on a source, and then n returns a new source where the range is basically source range start plus n to source range end. Something like this. Yeah, let's do that. So this then will be bacon.source without first parser cursor. And actually in the bacon we also did some crazy, yeah, right here. We didn't have a source yet. Yeah, okay, sure. Let's not do that here. Then. Okay, so here expected type expression. Yeah, let's create an error with that. Taking source without first parser.cursor. Okay. Yeah. Oh, here that actually fits the error message pretty well. Yeah, instead of doing this, I mean, we know the line is the context, so we'll just take the bacon source without the parser cursor thingy. Okay, what about this? I mean, that's a horrible error message. So if there are children, type definition, but it has children. Yeah, it's not really better, I guess, but you know, at least there's something. Ooh, what do we want to... Okay, I know the correct source. The correct source is a source from a range, which is bacon dot children dot first dot unwrap dot source dot range dot start to bacon dot children dot last dot unwrap dot range dot end. Underline all of the children and alright. True, it's not first, maybe. Yeah, underline all of the children and say, hey, this is bad. Sure. Yeah, same thing, basically. Just say parser like source dot parser dot source dot without first bacon dot source, yeah, without first parser dot cursor. Same thing here. Nice. Expected this thing. That will be this. Expected an arrow. Cool. Very, very cool. bacon.source dot without first parser cursor. Cool. And same here. Nice. Yeah, before we get to that, let's fix these down here. I'll just follow the errors. Oh. It would be kind of nice to just show this error at the... Yeah, that's just... Like, I thought maybe it makes sense to show the error at the opening parenthesis, but I think after that is even better. Oh, yeah, we don't have bacon. So we only have a parser, which means the parser, I think, should give us... It should contain a source, right? Like this. And this is actually the input source. You give it a source and it returns a parser where the input source is the source. Oh, it's even better than I thought. Imagine you can just say source of rest on a parser, and it gives you a source, and it's basically the parser input source without the first parser cursor characters. Damn, that is elegant. Hang on. Okay, let's actually remove without first. Yeah, because without first is kind of very specific for this use case. Yeah, let's remove that and instead just do, parser, I don't know, do you want a source? Just the input source range start to parser input source range end, and the start also got advanced by the parser cursor. Something like this. Oh, okay. Yeah, here we would give in the bacon sauce as well. No, too complicated. Just parser source of rest. And boom, you get a source that represents the rest, like the unparsed part. Damn, that's pretty neat. Yeah, when we create a variant, we actually want to use the source as well. And same here, just use the source. So these panic things we should fix that. But before we do, let's fix one of the other errors first. Nice. So cool. Oh, hell yes. Ah, that's nice. Cool. Cool. I don't really know which kind of people watch this stream. Like, this is... Currently I'm just relaxing, doing some grunt work, you know? Refactoring things. Like, for example, we can remove this, and then do this. This is really, really relaxing. Like, I don't know, doing a Sudoku or something. Just something where, you know, it's just a lot of constant keeping at it and not too complicated for your mind, but just enough to be relaxing. Yeah. So I'm not gonna talk too much. I'm just gonna let you relax as well. break silence. So I was thinking it would be kind of nice if the source also contained the entire input file. And that's pretty cheap because this string already exists in memory. So this is actually just, basically a pointer to that same string. And it's also pretty cheap to create. So in the bacon, we can just have a global variable, bacon. Down here we just have one variable for the entire content. Yeah, and here we can just say, well, this is the file content. And that's basically it. Now every source also contains content. Hang on, there were some cases here, I think, where the source is not in here. Yeah, where we create a new source from scratch. Oh yeah, but we can just take the input source content, yeah. Like file content. Mm-hmm. Oh yeah, so this is the same as, the bacon dot file content. Yeah. Basically, I don't really want to create new sources that often. Rather, I have something like with range, and we give it a new range. And yeah, basically it just creates a new source with, and instead of this, you have this. So it just creates a new source with the same file content, but the new range. So I only have very few places where sources are actually created from scratch. A lot of things are just modifications of existing sources. Because then over time I can also add, change this more easily, and maybe add the file name or module name, or I don't know what. Okay. Cool. Okay, so this is probably not working exactly, because here are some we could just call this like file content, or like no, okay. I'm fine with this. We could use the prototype pattern. Oh dang. Sure, let's do that. Prototype design pattern is following. We just create one source in here. With an invalid range. And then instead of creating new sources down here, we just say, you know, source prototype with range and new range. So basically we create a partially initialized object or value, and then we find that afterwards. Yeah, and these will all, like, I hope that the source constructor is never used here. For example, here we just use the parser input source with this range, and that's it. No need for creating a new range, a new source from scratch. Similar here, just take bacon source with range, boom. Right, that's it. No more errors. Apparently. Nice. Okay. Yeah, we create a lot of sources, so it makes sense that these are small. They just contain a single integer, and also like an offset into the content is really the simplest thing you can save. But when we write an error, we actually want to, I don't know, display the line number maybe, or even show an excerpt of the lines, like the previous 5 lines or something. We could do that. So how do we do that? I think we'll just okay, what do we do? I think let's try to show like the previous 4 lines maybe above the arrow, and the source code in them, and maybe even highlight the part of the line that's the error. Yeah. Okay. Yeah, let's do that. So, how do we do that? I guess first we create lines lines is error.fileContent.lines, and I think that's error.source.fileContent.lines, and that gives us a slice of strings. So the next step would be to find out in which line is the error, and also what's the offset of the error inside of the line. Var error line number is something I don't know, like for total offset it's 0, and then for each line in the lines we actually total offset is offset after is total offset plus line.len plus 1 because of the new line character. Perfect. Yeah, and then if the offset after that's less than the current, less than or equals, let's say, the error source start. We haven't found the error yet. We need to go to the next line and add that offset as well. Oh. Then total offset is total offset. Is offset after. Okay, otherwise we've found the error line. Yeah, let's flip that around. Yeah, that's more like it. I see. I guess just enumerate these, and yeah, let's do this in here because why not? Okay, no, let's put them there. Sure. Okay, found the error line. So here we have error line number, exactly, that's 0. And the offset in error line is 0 for now. And here we just say error line number is the index of the line, and the offset in the error line is the total offset, or like, sorry, error.source.range.start minus total offset. Then we break. So here we found the error line. Like, what's the index? Error line index is probably like yeah, I don't know. And we know the offset of the error inside of the error line. So now we can show the last 4 lines. How do we do that? We show the lines like this. So for line in lines.subslice. And what subslice? Well, the subslice from something to the error line index. Yeah, but including the error line index, right? Num lines is 5. And then well, that's kind of, we want to show 5 lines, but if the error is like in the third line of the entire file, then we also only want to show the first 3 lines. So it's basically bound by the actual line number of the line where the error is. And then we get the lines from error line index minus num lines to show. Including the error line index. This is an inclusive range. Does that make sense? If we only show one line, then this will be 1. And yeah, this will be 1 minus 1, which is 0, 0 to 1. Yeah, that's exactly what we want to do. You know, I love language constructs where you can break things onto multiple lines. Even if we have like a huge thing, we can just do this. And you always have an introducing keyword here. That's why I love for in do, where I like if then, you know. It's a really consistent design. Plus, of course, you don't need curly braces. Like most of the time, you can omit them. Anyways, for each line, we basically want to print, I guess the line number. First, line to show. Yeah, okay. Let's do this explicitly, because why not? This is the first line to show. Yeah. And then we just write down the line number, convert it to a string, like this, and pad it on the left, I guess, to 4 characters. And then we have the separator, and then the actual line content, which means lines.get line number. Oh, the number is 0 indexed. I guess that's fine. Yeah. And then a new line, and then below that the actual error message. Let's try that. Okay. Okay, we get an error, and then here we get a few lines. Expected this. That is Actually, that's one line too short. Like this is where the error is, and that's not actually contained in here. Why is that? I think we break too early. The offset after is larger than the error range. Let's maybe print the line error in line error line index. And yeah, these should be 0 indexed, so I guess 309. See here, 309 0 indexed would be this line, right? VS Code is 1 indexed, yeah. Not real programmers. No. 1 indexed lines. Well, okay, so then 309 0 indexed is actually where the error is. That's fine. Yeah, that's correct. But then it doesn't even print line 309. So the calculation was correct. But then down here, we do something silly. Oh yeah, if we only have one line to show, we want that to be the error index line, not the line before that. Yes, like this. Exactly like this. Okay, you know what, in the Plum, let's also just show line, oh no, an error. Okay. New line and then the error. And maybe also with a new line in front of that. And just immediately put that to standard error, because why not? More efficient than aggregating that into a string and then. Okay, oh no, an error occurred. And then you have error in line 309. Here is a snippet of your code, and this is the error. Can we like highlight that? We can just do, you know, write a. So we have 4 characters here, and then 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7. And then for each offset in the error line, we write another space. Yeah. And then for each character in the range, we actually write something like this. Yeah. Yeah, so this just highlights the rest of the line, which I guess is fine. Expected this. Cool. We have nice error reporting for some definition of nice. Yeah. Also, let's maybe not print the entire bacon. Yeah. And the toast and egg and yeah, like maybe, yeah, the yogurt is the important part, I guess. Like we should add some debug commands that can do that. But yeah, now we have our compiler, just run that, and we get, oh no, an error occurred. And then the error. oh no, an error occurred. Boom. Here's your error. Yeah, let's maybe add another new line here. And why are there new lines in front of that? With hello world, let's actually replace that with welcome to Plum, the Plum compiler. Yeah, I couldn't read file, that's fine. Yeah. Oh no. Why is there a space? Like a new line? Oh, because this is a print line, but there's also a new line. And we should use ePrintLine for, like, okay, so there, for tools, the common thing is that there are, like on Linux, there are two outputs for processes. There's standard out and standard error. And standard out should be the main output of your program. Like this should be the part that is piped into other programs, that other programs can read. This is the part that it should be machine understandable, and that's what the program usually, like the thing that you really want when you execute that program. If there's an error, that should, or like some human readable thing, that should usually be printed to standard error instead. Even if it's just, you know, a warning or something, still standard error. Or like a debug thing, standard error. Only the main output should go to standard out. Okay, yeah, so we underline errors. That's pretty cool. Yeah, let's not do this. And instead, yeah. Marvel at how this looks. Dang, that's pretty nice. I'm wondering, what if we do something silly, like here list, you know, length of a list returns true. Oh, it's not used right now, so it won't fail, right? Yeah, that's kind of bad. Okay, so let's maybe create a list of 1, 2, 3 and get the length of that, and that should fail. That's my goal. Yeah, so right now it just says couldn't join types. But really, we should get some nice, crazy error. And are there some, oh yeah, there are lots of panics in the toast still. So let's replace them. Replace them first and then continue working on the other compiler stages. So parse type atom returns maybe, although it really, yeah, it really should return a result. And parse type expression, does that really just return a maybe? Parse type atom, no, this returns a result. Yeah. So this also returns a result. Okay. And then parse type expression returns a result, or we return an error. Like, you know, bad input. Of an error that says expected parenthesized type expression with an error that is the rest of the parser. So parser source of rest. Yeah. Or return bad input toast type error. And yeah, this is somewhat inconsistent because, of course, yeah, some of these have a period at the end, some don't. Meh, kind of bad. Anyways. Oh yeah, same here. And this should be parsed. Yeah, this can fail, that's true. This should return that. Then in here parse, oh yeah, no, this can fail as well, which means this entire thing can fail with an error. Oh, this should not print additional garbage on that. Or maybe it should. But it shouldn't panic either way. It should just return an error. Of the error. And you know, the error is the source of the error is the rest of the line. Exactly what it says in the error. Cool. here we don't have a source anymore. So I think we just need to pass one in. Okay. Oh, yeah. Ooh, nope. No. I think the parser consume thing should actually return a source. That would be pretty cool. Yeah, let's do that. This returns a media source. so in this create var thing, if the left side is not a name, then we can just blame that on the equals sign. We can show the error there, which I think is fair. No error. Okay, yeah, compiles. Yeah, sure. So the rest of the compilation pipeline, of course, still just panics. And instead, we need to throw errors and also attach them to source location. Which means that these toast expressions here, they actually, like at least some of them also need to contain a source. Yeah, these expressions. Yeah, they may need to contain a source. Well. Yeah, let's maybe not do that today. Yeah, let's not do that today. Okay, so next thing would be the egg. And there are several tags in here, probably. Okay, not as many as I thought. Okay, so types apparently need, they need, we need to know where they come from. Same for names, and names again, and things. What even is this? Like, call, yeah. Oh, if a body is empty. Okay, no, I think this is actually like an unreachable thing. Sure. Okay, so there are some cases where we need to, especially this one, where do we want to show the error? If we have something like, let me see, 5, we call a 5. That's not valid. Do we want to underline the 5? Is the 5 the actual error? Or is the, like, really the call is the error, not the 5 itself? But the call doesn't really have a visual representation here. I think in Martinez, if you do that, you call 5 here. I think it underlines the, this expression can't be called. Okay, fine, fair enough. It just underlines the entire left side of that. Sure. mean, yeah, I guess that's reasonable. Just say this can't be called. Sure. But not today. Not today. Okay, yeah, let's maybe make this compile. So in here, just return 0. Oh wait, where was that? Here. And just make sure this compiles. Nice. And just for fun, let's also compile that another time and execute that. Beautiful. Super cool. Okay, yeah, I think we're done for today. We did some crazy things. We now have a garbage collector, even though it's like, it could be way more efficient, but still. We have one, that's cool. We have rudimentary error reporting. If you have an error in your code, we'll actually show you. Oh, is this verbose? We will sometimes show you, if it's a syntax error, we will just show you the exact location where the error is. That's pretty cool. And I think next session we'll just continue doing this. Some error handling. Maybe think about how to, create a better CLI. Maybe have different, have something like commands, and you can actually like specify a file instead of just the compiler always reading test.plum. Something like that. Yeah. Maybe have different commands like compile and debug, debug toast, debug yogurt, and so on. So you can actually we don't have to comment out code and comment that in, but we can actually just tell the compiler we want to debug this stage, and that works. That would be nice. Yeah, apart from that, we'll just see where this leads us, and I guess see you then.